In this section, we're going to learn about the mathematics of radioactive decay. Radioactive decay is normally described in terms of its half-life. The half-life is the average time it takes for one half of the nuclide to decay to something else. Actually, half-life can be used in many other situations besides radioactivity. So the mathematical definition would be this: the half-life, written as T sub 1/2, is the time for the number that you have now, which we'll abbreviate with a large N, divided by the number that you had originally, is N naught, is equal to a half. So after one half-life, N over N naught will equal a half. And after two half-lives, it'll equal half of a half, or a fourth. We can actually get pretty far in describing the mathematics of radioactivity simply by using that definition. For example, let's consider this. Let's say we have a basement that contains 3 times 10 to the 7th radon atoms. Now, radon is a radioactive substance that is given off by the cement that basements are made out of. Often we don't have a lot of basements down here in Texas, but up north this is a problem, and sometimes you have to put a system in your basements to get rid of this radon gas, because as I said, it is radioactive. If this radon has a half-life of 3.83 days, the original sample of 3 times 10 to the 7th radon atoms, how many would be left after 1 month of 31 days? We can proceed like this. 31 days is roughly 8.1 half-lives. We can just take 31 divided by 3.83 and get 8.1. And so, therefore, after 8 half-lives, we would have n times 1/2 to the 8th power, or 1 over 2 to the 8th, which is 3 times 10 to the 7th divided by 256. That would leave us with 1.2 times 10 to the 5th. Now, we can actually be a little bit more precise than that. We can use that same mathematics, but we just won't have to use the whole number of half-lives. So this is the formula that we just invoked a moment ago. But n, in the moment ago, we said, well, it was about 8 half-lives. But it could just be any number of half-lives. It could even be a fractional number of half-lives. So n is going to be the time that we have that has elapsed divided by the half-lives. So it could be some fractional number of half-lives. And then the number you have left is the original number times 1/2. And for convenience here, we're going to write 1/2 as 2 to the minus 1 power times the number of half-lives, even if it's a fractional number, to the number of half-lives power, I should say, even if that's a fractional number of half-lives. So let's see how this works in practice then, taking our original situation. But now we are going to raise 2 to the exact number of half-lives we have, not just 8, but we're going to raise it to a negative, because it's a half, 31 divided by 3.83, and then we'll multiply that by the original number of atoms we have, and we're going to get 1.1 times 10 to the 5th, a slightly more precise answer. Well, that's all well and good if you know what the half-life is, but how do we go about determining the half-life? To do that, we have to talk about the activity of a sample. The activity is basically, it's the number of radioactive decay events that you get in a given amount of time, just like we measured when we were looking at the differences between alpha, beta, and gamma radiation. It is measured in a unit called a becquerel, which just means a becquerel is 1 decay per second. So if you have 20 becquerels, that's 20 radioactive decays per second being detected. Now the key thing, the thing that's going to make this all work, is that the number of decays you get is proportional to how many of the atoms you have. It seems to make sense. The more atoms of a given type you have, the more radioactive decays of those atoms you're going to get in a given amount of time. So we say the activity is proportional to the number of atoms that you have, and the constant of proportionality is called the decay constant. So what we often are concerned about is not so much the total number of decays that have happened, but we want to know what is the ratio of atoms we have at one time to the number of atoms we have now. Well, that should have the same proportionality as the activity we had at one time to the activity we have now, because the activities are themselves proportional to how many of each type of atom we have. So we can use this proportionality here. The activity now divided by the activity at some past time should equal the number of atoms that are still present divided by the number of atoms that were present in the past.
Welcome back. We're going to do another experiment with a radiation counter today. We're going to see if we can characterize the half-life of polonium-210 by looking at the radiation that's emitted from sources that were produced at 3 different times. So we'll start out with the newest source, and then we will go to the later sources. This one was produced in May 2019. This time I am going to sit there and hold the sample up next to the radiation detector just so I can make sure that I'm getting the same position exactly each time, because that's going to be critical for our experiment. So once again, we are going to try to measure for a 50-second interval how many counts we get. And I'm going to put the polonium-210 sample in a position that I can replicate for the other two, namely right there. So it is held on the ground and it is held up against the side of the radiation, the lip of the radiation detector that's facing me. And I'm going to hit collect here, and we'll see what happens. Since these are alpha particles, I'm not too concerned about holding the sample in my hand for an extended period of time. As we saw in the previous experiment, alpha particles can be stopped just by anything, and there is a little plastic case surrounding these alpha particles. In fact, the back of the plastic case is open so that the alpha particles can get out and get into the detector. If it wasn't open like that, that little piece of plastic would be sufficient to block all the alpha particles. So I'm not in too much danger of being exposed to alpha particles right now. Okay, 1,693 counts in a 50-second time. Now let's look at the sample from March of 2018. And I'm trying to get the exact same position, held up against the edge of the radiation detector that's closest to me, and held on the ground. And I'm going to say collect. And there we go. And we're back, and we see that in 50 seconds, the sample that was made in 2018 was 180 counts in a 50-second interval. Lastly, let's look at the sample that was manufactured in February of 2015. And let's see how many counts per second this one, or per minute this one produces. And we'll hit collect. And it's 12 counts in 50 seconds. All right, that's data we need to see if we can characterize the half-life of the polonium-210.
So in the video, we actually came up with an activity for 3 different samples, and the samples we are going to assume are identical in size, and so the activity from different samples should be able to be compared as if they were the same sample at different times. But I'm only going to use 2 of the numbers because the third one, it turns out, I think the activity was influenced too much by the background activity. And so the results we got were very specious. And I'm thinking that we probably are, the sample is just simply too old to be a reliable measure of the activity of a sample of that size. So we'll just use the two that we have, but we can use the same formula that we've been using for half-life. We can say the activity now is equal to the activity at some time in the past times 1/2 to the number of half-lives that we've had occur. And the number of half-lives would be the time between the creation of the two samples divided by the half-life. So taking the log of both sides, that gives us the log of A divided by A naught. That's the activity now divided by the activity at some time in the past, is equal to a negative T over the half-life times the log of 2. Rearranging a little bit, we get that the half-life is equal to the log of 2 divided by the log of the ratio of the activities times the time that has elapsed between those two measurements. And plugging all those numbers in that you see up there and doing the solution, we get that the half-life is about 132 days. Now, on the samples themselves, it's labeled that the half-life of that polonium is 138 days. That works out to be a percent error of about 4.3. I should point out that we are going much farther into half-life than would be done on an AP test, but sometimes you can be expected to know this if you've taken a Physics 2 class. So let's talk about carbon dating. Now, carbon dating is a useful technique for dating things that contain carbon. So usually we're talking about living things. And they need to take on the carbon fresh when they were alive. Living things either undergo respiration themselves, they eat things that took in carbon from the atmosphere. And so this carbon is mostly carbon-12, but some of it is carbon-14. Where does that carbon-14 come from? Well, high in the atmosphere, you might have neutrons hitting nitrogen atoms, and when that happens, something like this can occur. So we saw a neutron produce cosmic rays coming in from the cosmos, or perhaps from the sun. Those neutrons turn a nitrogen nucleus into a carbon nucleus and release a hydrogen. Basically, a proton gets released. So now you have a carbon-14, but this carbon-14 is unstable. So now that carbon-14 will eventually decay back into a nitrogen by emitting an electron. That's a beta minus decay. So how does the carbon dating work? Well, the idea is that if the carbon or the nitrogen in the atmosphere is constantly being turned into carbon-14, and we assume that it's happening about the same rate in the past as it is now, then the amount of carbon-14 present in a sample that is living and taking in new carbon from the environment should be relatively stable over the centuries. In other words, the amount of carbon-14 present in something that when it's alive should be approximately equal to the carbon-14 that's present in something that's alive now. But once the thing dies, it's no longer taking in new carbon, and it obviously gets covered up, buried, not taking in new carbon. And so now we have that carbon-14 being converted back into nitrogen. So if you take a measure of the activity of a sample now and you compare that to the activity of a similar sample of something that's living now, similar size and everything, you can compare the activities just like we did a moment ago, and you can figure out if you know the half-life, what the time is that sample was not taking on new carbon, so to speak. So go ahead and do this problem right here. See if you can figure out an Ice Age human was found, and the tissues in this Ice Age human had an activity of 0.121 becquerels. A contemporary sample of the same sort of thing would have an activity of 0.230 becquerels. So therefore, how old is this Ice Age human if the half-life of carbon-14 is 5,730 years?